Last time, we looked at network slicing, how it's used, and the advantages it brings. Today, we welcome back Jimmy Dong to explore the technical architecture and working principles of the technology.
Hi everyone, it's good to be here.
Jimmy, in the physical world, we divide our highways and roads into traffic lanes by physically painting lines on them. In the virtual network world, what would be the equivalent? How is network slicing designed to make one physical network carry lots of different services that are isolated from each other?
Network slicing has three layers: an infrastructure layer, an instance layer, and a management layer. The infrastructure layer consists of physical network devices and links. To isolate the resources of slices, network resources need to be divided into multiple mutually isolated parts, based on required granularity, then provided for different network slices to use.
Is this like the dedicated lanes I just described?
Yes, you can think about it like that.
Okay. What's the network slice instance layer?
The instance layer is divided into resource slice and service slice sublayers. The resource slice sublayer uses node and link resources allocated by the infrastructure layer to form a virtual transport network. This is similar to integrating dedicated lane resources into a network slice map. The service slice sublayer provides logical connections for a group of service endpoints. This is equivalent to specifying start and endpoints for paths, as well as certain conditions for selecting paths. The network slice instance layer maps a service slice to a resource slice that meets the service's requirements. This is like using the dedicated network slice map to guide service traffic in the slice and using a dedicated lane for service forwarding.
And what about the management layer?
The management layer provides lifecycle management for network slices, including network slice planning, deployment, O&M, and optimization. This layer plays a similar role to a road management department, thinking back to the road metaphor we started with.
So why is network slicing realized in 3 layers?
Using layers, we can hide technologies in one layer from other layers, and flexibly combine these technologies to provide different solutions. The 3 layers include multiple technologies for realizing certain slicing functions. For example, at the infrastructure layer, typical technologies include FlexE, channelized sub-interfaces, and FlexChannel. At the service slice sublayer of the network slice instance layer, VPN technologies can be flexibly selected. And at the resource slice sublayer, both SRv6 and IPv6 enhanced technologies are available. The network slice management layer focuses on slices lifecycle management. It provides standard management interfaces without the need to be aware of the differences between implementation technologies at the lower layer. For different network slicing requirements, appropriate technologies can be selected at corresponding layers in the network slicing architecture to construct a complete network slicing solution, meeting the slicing requirements of different types of services in different scenarios.
You just mentioned that we provide multiple resource partitioning technologies at the infrastructure layer. How do we select an appropriate one in actual deployment?
Common resource partitioning technologies include FlexE, channelized sub-interface, and FlexChannel. FlexE isolates physical resources based on time slot scheduling. Interference between different FlexE interfaces is very small, so FlexE can be used to carry URLLC services that have high SLA requirements, such as differential protection services of power grids. Channelized sub-interfaces are logical entities created on a physical interface by using channelization technology. Bandwidth resources can be provided for them to carry different types of services. This ensures bandwidth isolation for services of different slices and enables different industries, such as healthcare and education, to be isolated. FlexChannel provides a lightweight resource partitioning in deployment mode, and is usually used together with FlexE interfaces or channelized sub-interfaces. Carriers usually use FlexE interfaces or channelized sub-interfaces to reserve coarse-grained slice resources for specific industries or service types. Within the slices for specific industries or services, Flex channel can be additionally used to reserve fine-grained slice resources for different enterprise users.
Flex channel can divide existing slices into subslices with finer granularity. Is this what we call hierarchical slicing?
Yes. Hierarchical slicing means dividing a network slice into independent subslices based on the more refined network requirements of users.
Where is hierarchical slicing used?
Currently, this technology has three typical applications. First, it provides tenant-level slices in industry network slices. For example, within the network slice for the education industry, independent slices for branch campuses can be provided for universities. Next, the technology provides application-level network slices in tenant network slices. For example, within the network slice of a hospital, independent slices can be created for different types of medical services, such as remote patient monitoring, remote ultrasound diagnosis, and medical image transmission. Finally, it provides network slicing services in a wholesale network slice. For example, a Level 1 network carrier provides a Level 1 slice for a Level 2 network carrier. The Level 2 network carrier further divides the Level 1 slice into multiple Level 2 slices for, let's say, the healthcare and education industries. This meets the requirements of different customers.
Okay, let's turn to consider the network slice instant layer. As you mentioned earlier, while mature VPN technologies are used at the service slice sublayer, emerging IPv6 enhanced technologies are used in the resource slice sublayer. What are the benefits of using IPv6 enhanced for network slicing?
The resource slice sublayer involves the control plane and data plane in terms of functions. The data plane needs to provide network slice identifiers and guide packet forwarding in slices. The control plane is responsible for distributing attributes, such as topologies, resources, and identifiers of network slices, to the slice controller and nodes in order to compute paths based on slice constraints. In the data plane, IPv6 programmability enables IPv6 extension headers to carry globally unique slice IDs, reducing the impact of network slicing on IP address planning or SRv6 seed planning. The IPv6-based data plane is seamlessly compatible with traditional IPv6 networks, facilitating incremental network evolution. In the control plane, IPv6 Enhanced makes only mandatory extensions to the existing IGP and BGP, minimizing protocol changes and avoiding the need to reinvent the wheel. In terms of scalability, IPv6 Enhanced inherits the characteristics of SRv6 without introducing path-by-path states throughout the network. This is very important for supporting a lot of slices.
When we need to support many different types of services, does the physical network need to be divided into many traffic lanes? Will this bring a lot of overheads on the network and affect the performance and stability of devices?
Scalability is indeed an important issue that requires careful consideration in the slicing solution. Configuring a large number of interfaces, sub-interfaces, or sub-channels for different slices on a physical network not only poses higher requirements on the forwarding plane capabilities of devices, but also affects the performance and stability of the control plane itself. Using IGP as an example, before network slicing is introduced, IGP generally needs to advertise only link state information of the physical network. However, if a large quantity of slices need to be created, IGP also needs to independently advertise topology information for each network slice. This brings lots of overheads to the network control plane. One of our experts in SR research first realized this issue, which led him to propose the concept of separating network slices from topologies. That is to say, multiple network slices share the same topology. So, the control plane only needs to advertise a small amount of topology information, and the result from only one topology calculation serves multiple slices, ultimately reducing the IGP load and improving IGP scalability. This idea of sharing a topology among multiple network slices is now widely recognized in the industry. In addition, in the data plane, the initial slicing solution is to allocate a group of SRv6 locators and seeds to each network slice as the data plane identifier of the slice. This is called the SRv6 seed-based network slicing solution. When the number of network slices increases, a large number of seeds need to be allocated. And given that the control plane protocol needs to advertise the seed information, this limits scalability. So, later, we decided to introduce globally unique network slice IDs as the slice identifier in the data plane. This slice ID-based slicing solution avoids the overheads that come when allocating many SR seeds to network slices, and it has become essential for supporting a lot of network slices.
In real life, when a road is congested, vehicles tend to switch from lane to lane in attempt to get ahead. When a network is congested, will different services similarly compete for resources? How do we ensure service bandwidth when designing network slicing?
This question is about resource isolation. We have two types of isolation, soft and hard. In the case of traffic congestion, cutting across lanes to overtake is likely to happen. However, if the painted lane lines on roads are replaced by physical railings, this can be prevented. This is also true for networks. At the beginning of SR design, the source routing function was emphasized, but bandwidth guarantees are mainly implemented through the centralized planning of controllers and bandwidth admission control for network access nodes. Since the controller cannot get accurate information about all service traffic in advance, and IP traffic is likely to burst, network congestion may still occur. And because networks do not reserve resources for different services in the forwarding plane, if congestion does occur, resource preemption is bound to happen. The result is that service performance will deteriorate. To implement the hard isolation of network slice resources, Huawei provides hop-by-hop resource partitioning technologies, such as FlexE and channelized sub-interfaces in the forwarding plane. Through this hard isolation, we can better guarantee bandwidth. In the control plane, logical topologies can be customized using certain technologies so that the application scope and the nodes and links of network slices can be defined on demand. Forwarding paths in the slices can then be calculated based on network slice topologies and other constraints. To sum up, the most basic attributes of a network slice are resources and topologies. A customized network slice can be obtained by flexibly combining the two attributes.
Thank you, Jimmy, and thank you for watching.